So in this video, we're going to introduce the notion of a power series. So first, what is a power series? A power series is an infinite series of the form summation k goes from 0 to infinity of c sub k times x to the k. And writing out the terms, we get the following. Which we can think of as an nth degree polynomial, where we also let the terms continue. More generally, a power series has this form. And again, we see the nth degree polynomial, where the terms continue. In this example, A is called the center of the power series. Before we move on, here are a few notes. We can think of a power series as a polynomial with infinitely many terms, or an infinite degree polynomial. A is called the center of the power series. The c sub k's are called the coefficients. And finally, the powers of x must be positive integers to be called a power series. That is, no negative or fractional exponents are allowed. So here's an example. The summation k goes from 0 to infinity, 1 over k factorial times x to the k. We can write out the terms as follows. And notice that our power series is centered at 0. Since 0 factorial is equal to 1, we can simplify a bit and get the power series 1 plus x plus 1 over 2 factorial times x squared, and so on. And notice we can see how our power series looks like an infinite degree polynomial. So why should we care about power series? One big reason will be that we can use them to represent functions when working with applications. For example, we'll be able to show that the function e to the x equals the power series above for all values of x. That is, e to the x is exactly the same as our power series. One of the main questions that we will be concerned with in this class will be, what is the domain of a power series? That is, given a power series, for which values of x will the power series converge? So we'll make the following definition. The set of values x for which a power series converges will be called the interval of convergence, or IOC for short. The distance r from the center of the power series to the boundary will be called the radius of convergence, or ROC. We can represent the interval of convergence and radius of convergence with a number line. Here is our interval of convergence, which will always contain the center, and the radius of convergence will be the distance from the center to the boundary. In class, we'll see how we can use the ratio test to help us determine the interval of convergence, or the domain of a power series. Before we do, however, let's get used to this idea of a domain for a power series with an example. Consider the power series k goes from 1 to infinity of x minus 2 to the k all over k times 3 to the k. Let's call our power series f of x to remind ourselves that we can think of a power series as a function. If we write out the terms, we get the following power series. Note we have a power series with center a equals 2. Now let's try to decide whether some given x values are in the interval of convergence for the power series. So first, is x equal 2 in the interval of convergence for the power series? That is f of 2 defined? We can find f of 2 by plugging in for x, and simplifying, we get 0 to the k in the numerator, which is the same as summing 0 in every term, which gives us 0. That is, f of 2 equals 0, or the power series converges to 0 for x equals 2. So to answer our original question, yes, x equals 2 is in the interval of convergence for our power series. Let's consider one more x value. So next, let's ask the question, is x equal 5 in the interval of convergence for the power series? This is the same as asking, what is f of 5, which we can find by evaluating our power series at x equals 5. Simplifying, we get 3 to the k in the numerator, and by canceling, we see we get the harmonic series 1 over k. And we know that the harmonic series diverges, which tells us that f of 5 is undefined. In other words, no, x equals 5 is not in the interval of convergence for our power series. So here's a picture of what we've discovered so far. Again, we can represent the interval of convergence of a power series using a number line. The center, x equals 2, was in the interval of convergence, but we also saw that x equals 5 was not in the interval of convergence. In class, we'll see in fact that the complete interval of convergence will be the interval from minus 5 to 5, including negative 5, but not including 5. So far we've been guessing and checking, and we'll need a more systematic method to find the interval of convergence and to check the claim above. We'll look at this in class, and we'll see how we can use the ratio test to help us find the complete interval of convergence for a power series.